7 is going to be cut because I have to cut back on the test because it's too long. We have to be able to solve it within our lifetime. So I'm going to take, that one's going to get the axe. The first 7, which is the kinetic investigation. The reason being, we've already had enough kinetics here. So I'm going to cut question 7, which is the kinetic investigation of A2 plus B2 going to 2AB, etc., asking you to find the rate law and the rate constant, etc. Question 10 is going to be cut, and I think it's the only 10. Let me check. It is, okay. That one's going to be cut as well, because it's another kinetics question. I got to have something other than kinetics here. Okay.
You really don't need.
Wait. 10 was what?
Kinetics solving.
Yeah. 10 is
Kinetic investigation.
Kinetic investigation of the temperature dependence of a second order process. That. Wait, let me see about, before I answer that, let me look and see what 8 you're talking about.
You're on camera, so don't screw up.
Okay, number 8. Now 8's being a 7, 8. Oh, yes, both 8's. Now, the second 8, because it was a typo and I had 2 8's, that one is another kinetic question. It's being cut. Okay. Now, the first 8, which is a biggie.
Wait a second. Are you...
Okay. Let me slow down.
A and B, is that what you're talking about?
Which one? Yeah, 3A plus 2B. Going to C. That's the second 8.
First 8 in it.
Okay, the first 8 is going to be cut. The first 8, which is the one that everybody was lobbying against, which is the calculate the molar solubility of silver bromide in ammonia. The first 8, yeah, that's the first 8. On the key, I have the different numbering. On the actual test. The 8. Okay, I'll see where it is on the key.
Yeah, I'm looking at the key, and that's totally different.
Different copies.
Are you saying those 8 on the test are going to be cut?
This one is cut.
I'm looking on the key now. Yeah, 8 is going to be cut. And yes, both 8's are going to be cut.
Oh, okay, yeah.
So the 8, the one that everybody was really lobbying to have me cut because it would give us more more time to work on all the rest of the test, was the molar solubility. It is going to be cut, but be advised of the following. The reason I had that there to begin with, that's not a kinetic question, that's an equilibrium question, and it's a really good one. So the concepts contained in it, the conceptual part, comprehensive part about equilibria, that I'm going to now absorb that question into a couple of multiple choice questions or true false. So I want you to at least be familiar with the underlying concepts involved in that question. And I'll review the question. I'll review the question here. Yeah, what you do with the equilibrium constants. If I add 2 equilibrium together, 2 equilibria are coupled. In other words, if I have the product of one equilibrium being a reactant in another one, they're thermodynamically coupled by that. So first of all, recognize that that's what thermodynamically coupled means. And second of all, what do I do with the equilibrium constants? You multiply them. What would I do with the free energy? I would add it. As you do. We know that from Hess's law. Okay, so if I add the free energy, what would I do with the pKs? I would add the pKs. But now with the Ks, the mass action laws, I multiply them. So if I add the free energies, I multiply the mass action. That's a complicated way of saying it.
We have that on chapter, on the second one.
You see, if I add two equilibria, I multiply the equilibrium constants. And the equilibrium constants, the word I've been using for that has been mass action expression. So I just want you to be familiar with that. I'm not trying to bog anybody down with language. But you've heard me repeating the mass action a lot. You've been hearing it, you've been saying it yourselves. The equilibrium constant is the mass action law. Okay? And so if I add equilibria, I multiply equilibrium constants, or I multiply mass action. Okay? So that is something that could easily find itself in those well-loved and adored multiple choice questions. Okay, so that's how I'm going to absorb it. And that gets you around, because the problem with that problem was people bogged down on the math. And it wasn't, you know, although I'll review it, because the math isn't anything you guys can't handle. I've seen you do it. Like I said, you guys have taught me a lot this semester. And one of the things I've learned is that you're more than capable of handling this. Okay? So, you may not think so, and I don't want you to be intimidated or afraid of the test. You guys are more than up to this. Just relax, take your time, and you'll do fine. Okay? Now, so, number 8 is going to be cut. What other ones am I cutting?
Number 7.
Number 7, yeah, we cut number 7. Somebody said, oh yeah, 10 is being cut. Now, I'm going to keep 13 and 14, and I'll get to those in a little bit. Okay? But before we get there, I want to jump right back in, and now I've shuffled all my papers.
Wait, which 8s got cut?
Both of them.
Isn't there 3?
Is there,
On the key, there's 3 of them.
on the key, there's 3? Oh,
Yeah,
course.
3 8s on the key are cut.
Oh no, you're right. There he
I
is.
need to quit looking at that.
Right here, dude.
And all 3 are
There's
cut.
another one. Yeah.
Okay.
All 3 of the 8s on the key are cut.
Okay.
Okay, so
Good.
8 is gone. It's the late 8.
How about we cut 13 and 14 and keep a couple of those 8s?
No, 13 and 14 are necessary because they're elementary thermodynamics. Okay. Okay. We have to measure across the spectrum what we've done all semester. So we need some equilibrium and we need some thermal. We've had enough kinetics. Okay? Now, back to where we're going with this. Okay. If I can find my actual test. Okay. Was there a question?
No.
Okay. Now, let's take it. Let's do a little one just for to ease back into the process, because we've done a couple of biggies so far. So the nice one is actually question number 2 on the actual test, and that is the enthalpy of fusion for a compound is 150 kilojoules per mole. The melting point for the compound is 27.0 degrees Celsius. What is the entropy of fusion for compounds. Question mark. Now this is really should be a gimme, but one of the things I wanted to sort of before we answer this question, why is it so easy? What is melting and freezing? What kind of a process is that? It's a what? It's a multi-syllable word. Sounds like. Let me see. It's 5 syllables. Sounds like, and I'm not going to be able to do this one.
Thermodynamic?
No. It's a process that we studied a great deal about. Right after we did thermodynamics, we derived
That doesn't narrow it down.
mass action describes what kind of processes?
Elementary?
The law of mass action is what kind of that? What was that word I heard? No, I heard a word here. Equilibrium. 5 syllables, isn't it? Equilibrium. Yeah.
I can't count.
I have trouble myself. We got to get spell check in on this. Okay. So it's an equilibrium process. Now, since it's an equilibrium process, what do we know? What is the free energy, delta G, for every equilibrium process? Yeah, but it's equal to, what's it equal to? 0. When we reach equilibrium, there is no further driving force. Remember Le Chatelier and all that other good stuff? And since it's an equilibrium process, this is on scratch paper before we answer the question. Delta G is equal to delta H naught minus T delta S naught, and I'll put a little tilde over this to say that it's approximately equal to that, and the reason being that under non-standard conditions, the enthalpy and the entropy usually don't vary as significantly over a temperature range, and we can take advantage of that over the temperature range in question. So delta G is approximately equal to delta H naught minus T delta S naught. And I'm going to use a double arrow to denote equilibrium. Delta G is equal to 0. Therefore, delta H naught is equal to T delta S naught. And that enables us to answer this question. Okay? And so, therefore, I'm after what is the entropy of fusion. So delta S naught of fusion is going to be equal to what?
Delta H over T.
Over T of fusion, or the melting point. So now we can answer the question. So the answer to the question is delta S naught fusion is equal to, what was the enthalpy of fusion? 150. Now, another key point, it's going to be okay if you use kilojoules or joules, but the standard notation, as you'll note in the thermodynamic tables at the end of the book, is for entropy only, it's denoted in joules per mole per Kelvin. So I like to convert 150 kilojoules to joules divided by, and 27 degrees Celsius. So on scratch paper, you go 27 degrees Celsius is what?
300 Kelvin.
Yeah, over 300 Kelvin. And so I'm going to just, you could write this out on scratch paper. I'm going to do the scratch paper over here. It's going to be, let's do,
Don't forget the moles.
joules per mole. Thank you. Thank you, Chris. I'm going to go ahead and convert this to some sort of scientific notation, like 1.5 times 10 to the what? 1, 2, 3, 4, 5 joules per mole divided by, and 300 K, I can go 3.0 times 10 to the what? 2.
15 times 10 to the 4th.
Yeah.
What?
15 times 10 to the 4th would be easier.
Oh, 15 times 10 to the 4th? Yeah, I like that. It'd be even better. Let's do that.
This should be a 100-point question.
No, I'm just, this is, see, the whole reason for scientific notation is it makes things, it casts things in an easily soluble form so that we can handle it. Now, all I need to know is I need to be able to divide 15 by 3, which is equal to what? 5. I'll put it as 0.0 just for fun, times, and now I've got to deal with the rules with exponents. What do I do when I divide 10 to the 4th by 10 to the 2? You subtract the exponent, so what's that? Times 10 to the what? 2. And now the units are going to be joules per mole per K. And I'm just written off the board. Can you see this part? I'll just put the K under here. Okay, and now I'll write it over here. Equals, okay, so now that I've got it in that form, let's write it in something that's a little bit easier to understand. What's 5 times 10 to the 2? 500 equals 500 joules per mole per K. Okay? So this is, in fact, this is a gimme. I guarantee a question like this. I'm either going to give, I'll give you I'll either give you the enthalpy and the entropy, or the temperature and the enthalpy, or the temperature and the entropy, and I'll ask you to solve for the third. So you see how easy that's going to be. If you just relax and try to relax, I don't know any magic words that help that, but whatever helps you.
Like bring your notes or good words?
No.
Drink a beer before.
Well, actually, the best thing I could suggest is breathe in through your nose.
Tried that, doesn't
Did you say that the final was available?
You tried that, it didn't help, huh? What?
Did you say that the final is available over there at the tutoring center, that we can take it when we need, when we die? Is that true?
I can do that.
I heard that. That's what you said.
I was gonna.
No, I
I
remember.
heard that's what you said.
That was something. Yes, you heard that, and I did in fact say that. I have not put it over there yet. I thought I'd give you guys a chance to go through this recitation and give you up till Tuesday.
Yeah.
But is there anybody here who wants to take it real early?
No, but if we want it, want to.
You want it now?
Maybe.
Well, I can't give it to you right now.
Not right now.
I'm going to go home and write this after this feedback.
Can we take
So
it on
maybe
Monday
Monday.
over there if we wish?
I can. I'll put it over there.
That'd be cool.
In fact, I can put it over there Monday if you like.
Very nice.
Yeah.
Would you guys like that?
Yeah, Monday morning.
I'll put it over there Monday
And our
morning.
deadline to get it completed is when?
The deadline to get it completed is going to be by Tuesday.
When this time, like at 7 or?
Tuesday night. Because the time we're going to be taking it is Tuesday. Okay. What? Yeah. Yeah. Is that cool? Is everybody clear with that? The test, the final will be available at the testing center Monday.
And you want us to be
Yes.
done by 7?
What time's the final on Tuesday?
It was 5:15 is the official time for the test. I'm going to be available here at 4 o'clock because there are some individuals who are pressed with time. And so I'll be as early as 4 o'clock, but the official time for the official sit-down formal, wear a tux. The official time is going to be 5:15 through what? 7? And if anybody has to go into extra time, I'll hang around. So I'm not going to push anybody. I don't want time to be the problem. I want to get an accurate measure of how much you got.
But if we want to go there, we can.
Yeah, but practice it so you guys should be able to handle this with you know what problems are going to be cut, what's going to be kept.
Cool.
So you get comfortable with it and try to relax. I don't know how you do that. Whatever works for you. Try breathing. I don't know. So try to relax and you should do well. So this is a gimme problem. Now let's get to one with a little more meat to it. This problem is problem 3. And so I'll do that one over here. This is an absolute, for sure, going to be on the test, and it's a big point problem because this covers both thermodynamics and equilibrium and acid-base. Okay? So this is a very comprehensive problem. And so given okay, I'm giving you this information. You recognize it. This is what?
Acetic acid.
This is acetic acid. This is something we've seen a lot of. And I want to note that it's not a typo. The free energy of formation of water is the same as the free energy of formation of the hydronium ion.
Is hydroxide the same?
No. No, that's different. But this is going to be convenient when it comes to actually calculating the free energy for the process. So A, what did I ask you to do? Find delta G. For the reaction. And so, what is delta G formation?
Products minus reactants.
And each multiplied times its corresponding stoichiometric coefficient. In this case, that's going to be kind of trivial because their stoichiometric coefficients are all 1, which is kind of nice. But you have to recognize that fact. And your note, the math is going to be very greatly simplified by the fact that the product and reactants happen to have the same, but I do not want you to omit anything. A lot of it is going to be in the detail of your answer, and so delta G naught is going to be equal to I'm going to have 1 mole of hydronium ions, and there is minus 237.18 kilojoules for every 1 mole of hydronium ions, plus 1 mole of acetate times minus 369.31 kilojoules for every 1 mole of acetate ions equated. And now its products, what? Minus reactants. Now, last time somebody brought up, I could just put brackets here and then add the reactants. I mean the reactants to it, the free energy of formation of the reactants. Or I can just absorb this minus sign in. Either way, as long as you're clear, you're going to get full credit. And you're going to get full credit if you include all full detail. That's what I'm looking for. So minus, I'm going to go 1 mole of acetic acid, and there's minus 396.46 kilojoules for every 1 mole of acetic acid. And then I'm going to go minus 1 mole of water, and minus 237.18 kilojoules for every 1 mole of water. And that statement alone gives you almost all the points. The last part of this is you have to actually do the calculation. And so now you can take advantage. And like I said, if you put this in brackets and added these, that's okay too. As long as you're consistent and try to write clearly. Now, this is going to be equal to
27.15.
Okay, let me get there a little bit.
Sorry.
That's okay. No, very good.
Math takes time.
You're faster than I am, and that's a good thing.
Actually, though, we're kind of like short on time, so can we just...
Okay, we'll cut to the chase. Okay, this is equal to, what was it you told me?
27.15.
Equals 27.15. 15 kilojoules per mole. Okay, so we are pretty much, that answers part A. Since we're short, what?
Isn't it just kilojoules?
Yeah, you're right. It is just kilojoules. Oh, yeah, although it would be kilojoules per mole.
It's kilojoules per mole.
Because the moles cancel.
Oh.
Yeah, it's just kilojoules. You're absolutely right. Okay. So, now, part B. What is pK for the reaction? And pK is going to be equal to, yeah. So the answer to that one, and I'll do it in blue, pK is going to be equal to delta G naught divided by 5.7 kilojoules.
Is that a constant?
Yeah, because it's delta G naught denotes standard conditions, which is 25 degrees Celsius. And at 25, so on a piece of scratch paper, just for your information, 2.303 RT is equal to 5.7 kilojoules. Okay, and that's from whence that process came, because R being 8.314 joules per mole and T being 298 Kelvin. you can punch it through, and it's going to give you 5.7 kilojoules or 5,700 and something joules. So we can just take advantage of that and solve for pK. And so pK, that's equal to, what was it, 27.15 kilojoules divided by 5.7 kilojoules equals, and pK has to be unitless, it's an exponent, and that turns out to be, what was it? 4.76, which you work out on a separate piece of scratch paper. Okay? And, you know, so that part's not going to be a problem. This would be on, this doesn't go there, but it's on scratch paper. Okay? Now, part C. What is mass action? Or find, no, it's find K, sorry. Okay, and this turns out to be almost trivial. What is K? 10 to the negative pK. So K, let me get my blue pen. So K equals 10 to the minus pK equals 10 to the minus 4.76. So that answers that question. Okay? Now, for the next part, I'm going to have to go over to one of these boards. And just give me a second to erase. And well, this looks like it's going to take a little space, particularly since I'm writing the question. Okay, consider the titration of 100 mils of solution. So this is part D. Okay, this takes me almost longer to write the question out than it's going to probably take us to solve. This is pretty straightforward. First we have to do what? We're going to hit the ice, but I need to write. We're going to check to see if our approximation is going to be valid, but I have to write the reaction out so I can do the ice. So I have. I'll do this in a different color to distinguish it. to write that out. And then over here on the corner, I want to see if my approximation is going to be valid. And what do I have to know for that?
Divide your molarity by your K.
Yeah, I have to divide my molarity by my equilibrium constant. And if it's greater than
10 to the 2.
100, yeah, 10 to the 10 squared or 100, then my approximation is going to be valid. And so that is, my molarity is 2.0 molar. Now, it's going to be more convenient if I express the molarity in what form?
10 to the 0.301.
As a log, as we're going to be doing throughout this problem. And what is the log of 2 again?
0.301.
Where'd you grab the 2 from? The acetic acid or the sodium hydroxide?
Both, yeah.
No, which one?
I'm using the acetic acid.
Acetic acid, okay.
Yeah, yeah. So the concentration of the acetic acid. So 2 over 10 to the, what was it? Negative 4.76 is equal to 10 to the 0.301 divided by 10 to the minus 4.76. And that is equal to, okay, over on my scratch paper I go 4.76 and I go 0.301. Okay, that's a 9, that's a 5. And that was going to be a 4. Okay, equals 10 to the 4.459, which is much greater than 10 squared. So this is about 10,000. Actually, it's actually closer to what? 0.459, awful close to 3, isn't it? So it's around 30,000. 30,000 is bigger than 100. So our approximation is valid. Okay. So therefore, approximation is valid. And now I have to write, I'm going to hit the ice. And so the ice is going to be I, C, E. And I have 2.0. What's my initial value for hydronium ion? 0. And acetate? 0. What's the change? Minus X. What? Plus X. How about here? Okay. And so I have 2 minus X, X, and X. And now, at equilibrium, K is going to be equal to, so 10 to the minus 4.76 is equal to X times X divided by the mass action expression, 2 minus X. So it's going to be X squared over 2 minus X. And our approximation is that this is approximately equal to X squared over 2. And therefore, X squared is equal to 2 times 10 to the minus 4.76, which is equal to 10 to the, what is 2? 10 to the 0.301 times 10 to the minus 4.76, and that turns out to be equal to 10 to the 4 or minus 4.459. So we've already done all that heavy lifting. And now, since we know this, I know that X squared is equal to 10 to the minus 4.459, and therefore X is equal to 10 to the minus 4.459, the square root of that. And what do the rules with exponents have me do? I multiply 1/2 times that, so I get my scratch paper over here, and I take a 2 and I divide it into 4.459, and it's 2.22, and then 9, okay, 9.5, and we'll get to rounding back to deal with the significant figure convention here in a minute, but that means that's equal to 10 to the minus 2.2295, and that's equal to the hydronium ion concentration. Okay? And therefore pH, what's the P of anything equal to? Negative log base 10. pH equals negative log base 10 of 10 to the minus 2. I could adopt the significant figure convention. How many figs am I limited to in the given data?
1.
Well, 2.0. So 2. Okay, and when I'm talking about logs and exponents, how do I count sig figs? Does the number to the left of the decimal point count? No, it's only to the right. So I have 2 to the right of the decimal in my significant figure convention. So this is going to contain 2. What's my rounding convention say about that? 2.23. So it's 2.23 equals 2.23.
You can dock us for sig figs.
I'm really not that concerned about that. If you handle all the rest of it,
Okay.
I'm a happy camper.
Excellent.
Because this is a really good comprehensive question. But, you know, it's one of those sensuous things. Since you was here already and we got all this other work done, we might as well. It's not going to hurt, but don't agonize over this and start, you know, freaking out and worrying about it, and to the point where you're not going to get the next question. So just relax. Believe it, you're doing some good work. Okay, now for part E. Well, I guess I'll do part E over there. Because I don't want to crowd the board. So part E. What is the pH after addition By the way, what kind of a equivalence point is this? This is a quarter equivalence point. I've added a quarter of an equal molar amount of base. Okay, and so we're going to need what equation? What famous name equation? Henderson-Hasselbalch, which you guys can all derive from the mass action law. And pH is equal to what?
pKa minus the
Log of, it's going to be HA, or the protonated form of the acid, divided by the conjugate base. Okay? And so all we need to do is therefore solve for that. And that's equal to 2.0 moles per liter, because it's 2 molar, times, how many liters have I got? 0.1 liter minus 0.025 liters divided by what? 0.1 liters plus 0.025 liters. That's the upper part, all divided by 2.0 moles per liter times 0.025 liters divided by 0.1 liters plus 0.025 liters, and Gesundheit, whoever sneezed. And so all of this nicely drops out, and we're left with this is equal to what, 0.1 divided minus 0.025? 0.75 divided by, and the liters divided by liters drops out too, by 0.025, and that's equal to what?
3.
3.
Are you going to dock us if we don't write out that whole mess?
You could do most of it on scratch paper, and I'd be happy, but the only reason I would want you to write this all out is because I might not give you the quarter equivalence point. Let's say I gave you the third equivalence point instead.
Me too.
I know. but and you know too. See how good you guys are getting at this? I'm not worried about you guys. If you can just relax, you'll do fine.
Well, that's fine, but we have to write all that out at the same time.
Dr. Fletcher?
Relax.
I'll take it. I'll take it if you don't write all this out. If you just cut to this. But it's a yes.
What if
David.
you started with base instead of acid? Would you have OAC over HOAC instead of your log there? If you started with base instead of acid. Yeah.
Oh yeah. I mean,
Okay.
but we'd have PKB.
Same thing.
We'd be doing POH and PKB, and then we'd have to. Then what relation would we use to find the pH? I'd be solving for POH. 14 minus POH. Yes.
OAC over HOAC.
Yeah, because again, we derive the Henderson-Hasselbalch expression from the mass law expression. Mass action. Okay, so now we've got this, and now we can solve, and the pH, and yes, we can omit all this gobbledygook, but don't be worried about writing it if you feel like it. If it makes you feel better, just go for this fact, and pH is equal to pKa, which is what? 4.76 minus the log of 3. And what is the log of 3? 0.477 equals 4.76 minus 0.477. And so over on my scratch paper, this is scratch paper, 4.76, because I'm kind of slow, 0.477, and that's 3. This is 5, 15, which is 8, and this would be a 6 minus 2. That's 4 equals 4.283. What? No, because this is 15. I had to borrow. My credit's shitty too. I'm sorry. Okay, I had to borrow from the 6 here. Okay. Okay, now if I'm going to stick with my sig fig convention, what is this going to be?
4.28.
Yeah. Okay. So that answers that problem, and that is pretty much the end of that problem. This is a big problem. Okay? So is everybody cool with this one?
Yeah.
Any questions? Okay. Well, I don't know how many points it's going to be, but it's going to be some points.
75 points.
10, 20, 30, 40, 50 at least. That's about a 50-pointer. Okay. I want to go on to, I could do the multiple choice, or the multiple guess true false, but I'd rather get to one of the working problems before that. And so, which one was I going to? After 3, the counting shall be 4, and then 5.
Second 5.
Okay, we've done 5 already. The second 5, second 5, which is a gimme, and it's electrochemistry. So let's go over to, you're already named on this board. I'll do it on this board. Okay. And the second 5, the first one, which was deriving the derivation, which we did to start with. Second one is an electrochemistry problem, and it is okay. The question probably take us less time to solve than it took me to write the thing. How many grams of copper will be lost from the anode of an electrolytic cell that is run at 0.02 amps current for 965 seconds? Recall that the atomic weight of copper is 63.54 grams per mole, and 1 Faraday is equal to 9.65 times 10 to the 4th coulombs per mole of electrons, and that copper is oxidized to a copper 2 plus 2 electrons. Okay? So that's all the information needed to solve this problem. It's pretty much almost a one-stroke solution. It's going to take us one line to do, and maybe 1 second line to write the answer. So what do I start with on the left-hand side? Seconds? So I prefer to write this out as 9.65 times 10 squared seconds, just to make the calculation clearer. Okay, what do I go from? I'm going from seconds to what? Coulombs. Okay, and where's the coulombs buried in this? Okay, amps. What's an amp? A coulomb per second. So I have, and I'm going to write this again, 2.0 times 10 to the minus 2 coulombs for every 1 second. 0.02 amps. Again, the scientific notation is going to make life a little bit easier. Okay, and now I go from coulombs to what? moles of electrons. And what do I use?
Faraday.
Okay, 1 Faraday, which is, there's 1 mole of electrons for every 9.65 times 10 to the 4th coulombs. So that's the charge on a mole of electrons. Yes?
On the key, are you missing the...
On the key, I had a typo. And instead, I didn't put .02, I put what? 2. Okay. That we're correcting right now. Okay? Yes? Oh, I thought you were just drinking. I thought you were raising your hand, you were raising your drink. Okay.
Cheers.
Okay. Now, all hail the infant king and his uncle the regent. Okay. Okay, now, I'm now in moles of electrons. What do I do next? Moles of copper. There's, and what goes on top? 1 mole of copper. What goes on the bottom? 2 moles of electrons. And we got that from this information here. And what do I go from now?
Grams.
And there is 3.54 grams of copper for every 1 mole of copper. This is basically a Faraday's law question. Okay? Michael Faraday. And so, and this is where it's a one-liner. And then we're on the next line we'll write the answer. But let's walk through the calculation. Okay, well, 10 to the 2 times 10 to the minus 2 is what?
0.
1. Okay, yeah. It's not quite enough.
Well, if you 10 to the 0, which would be 1.
Yeah, 10 to the 0, which is 1, yes. Okay, very good, thank you. Okay, and now I've got 9.65 divided by 9.65 is
The trash also.
1. So then I've got
That you saw at 2.0 and that 2, so that can.
I've got 2 divided by 2, which is 1 again. Now I have 10 to the minus, or 10 to the 4th. I have all this business divided by, so I've got basically 1 divided by 10 to the 4th. What is that? 10 to the minus 4. Because when you divide by an exponent, you just subtract. Okay? So, and now all of this, so I've got 10 to the minus 4th times 63.54. So that's equal to, I'll write it out, equals 63.54 times 10 to the minus 4 grams. And then, I'll put a little copper here. And then, we'll write it on the next line.
That's a nice setup.
So I move this. Well, I can write it.
That looks good.
You like that?
Yeah, that's good.
Well, if I want to use scientific notation, I'd go.
You're already using it.
I'd go 6.354 times what? 10 to the negative 3rd grams of copper. And that would be an excellent answer.
Dr. Fletcher?
Yes.
On your key, you made a mistake. Just because you
There's a shock.
you said it earlier, but might as well get it on tape.
Good point. Yes, absolutely.
Yeah, it's just on the coulombs you put 2 instead of 2 times 10 to the minus 2.
Okay.
So
Very
that's the
good.
difference.
Thank you. Thank you.
That's the camera can hear.
Thank you. Yeah, there was a typo on the key, and it was I put
Right at the coulombs, it was 10 to the, put 2 instead of 2 times.
I put 2 here, and I left out the 10 to the minus 2.
And the answer was off by a factor of that as
So
well.
the answer was off by that corresponding factor. Yes.
Where did the 2 mole come from?
2 moles. 2 moles of electrons came. That's a very good question. He asked where the 2 moles of electrons came from, right? 2 moles of electrons. It's going from copper to copper 2 plus. Okay? When in such an electrolytic cell, where the copper plus 1 turns out to be unstable to its disproportionation, so it would be copper plus 2. And whether it's a 1 electron process or a 2 electron process is actually found by this type of an experiment. This is a Faraday's law experiment. This is how Faraday originally made such discoveries. Okay? Does that answer the question? Okay. And thank you for that. Okay. Any other about this one before we move on? We're good to go?
Yeah, you made a mistake on your key.
Are wormholes real?
We talk about Farscape.
We talk about what?
Farscape.
Okay, Farscape. Okay. Well, yes, I will have some South Park questions. And okay. Now, question number 6, which is a nuclear chemistry or nuclear question, which is appropriate in this particular time, very poignant time, where we had a recent episode in Japan, and my wife is worried about whether we should be buying tuna. Oh, don't worry about buying. If I were buying tuna, I'd get a Geiger counter. That's all. Take a Geiger. They'd wonder what you were doing in the Isle of Bonds with the Geiger counter. Yeah. Homeland Security take you down. Okay. Complete.
Question in the back.
What?
Are you doing the periodic table on the test?
Yeah.
Yes.
Okay, sure.
That's a very good question, and I have to remind myself, thank you for reminding me, I will include a periodic table. Complete the following reactions. Okay, this is the one that gives us the carbon-14 in the upper stratosphere, neutrons from the sun bombard the nitrogen, which, what's the composition of the air up there? Is it the same or different from the composition of the air down here? It's the same. Okay. So we got about 78% of the air is nitrogen, and it gets bombarded by neutrons, and that gives us some sort of carbon-14 plus what? Plus a what? What goes here? So conservation of atomic mass number gives us a 1, and conservation of charge number gives us a what? A 1. And that turns out to be a proton. So these are pretty straight up. The next one is what I would expect in my little underground bomb factory where I'm...
You're on camera right now.
I would expect a knock on the door. 235, U-235, 92.
You making suitcase nukes, Fletcher?
Yeah, well, no, shoes. Much better than
Suitcase.
more fashionable. Gives me 144, 55 cesium. plus what? So when U-235 sloughs off a neutron, it's going to give me to fizz to give me cesium. Or when U-235 doesn't slough off, when it's bombarded by a neutron, it's going to give to fizz to cesium 55. 55 cesium plus what? So I got over my scratch paper 235, 144, 1, and then that becomes a 9. Oh, plus that, yes. So it would be 236. So it would be 92. Thank you. Who said that? Thank you very much. I did that back. So I reproducibly make my mistakes. Okay.
Not correcting your mistake. No.
Okay. 92. And then on the for the atomic charge number.
37.
Okay, yeah, it's 92 minus 55. It's 37. Okay, so 37 tells me what the atomic number is. It's rubidium? Okay. As can be seen by the periodic table, which will be provided for your dining pleasure. Okay. What?
This would still break down a lot of it.
Oh, yeah. This is just... what usually happens is there's going to be usually some sort of a an unstable, and all the trans-bismuth elements are unstable with respect to sloughing off neutrons, among other things. And so one neutron is going to initiate a fission event, and it's usually going to give you more than one nuclei, like this, plus more neutrons, and that initiates the chain reaction. You get a cascade and a feedback mechanism that gives you either a China syndrome type meltdown, or if the right critical mass is there, an atomic bomb. Okay. Let's see, so number C is, one of the fusion processes. I take a tritium plus a deuterium. I slam those together like is going on the sun even as we speak, and I get a helium plus what? So my atomic mass number is 5, so what does this have to be? 1. And my atomic number, my charge number is 2, so what's this have to be?
0.
And that corresponds to what? A neutron. Okay, so we balance that reaction. And the last one is another fusion process. Another one that is cooking even as we speak on the sun. I take a beryllium 4, or beryllium 8, I'm sorry. My bad. Beryllium 8.
The helium's an alpha particle, right?
Yeah, this is an alpha particle. A helium nucleus. Helium 4. Plus a helium 4, now that you mention it. So I have a helium, so the nucleus synthesis that is occurring on the sun, I can take a tritium and a deuterium, slam them together, and get a helium, and then I can, through the synthetic process, if I took 2 heliums and slammed them together, I could get a beryllium 8 nucleus, which is a very, very short-lived, unstable nucleus, but doesn't have to last very long, because it can then combine with a helium 4 to give me what? Wonderful element. 12, and what's that? 6 carbon. This is proposed to be the mechanism by which nucleosynthesis produces carbon in stars, which is where we got the stuff that we're made of. So we're all basically solar radiation with it got together. They're solar processes, all solar energy. Okay, now question number 7, cut.
Yay!
Now question number 8, cut.
Wait, which number 7? Oh, not the second one?
The first one, where's the second 7?
Easiest one is after number 8, before the second 8.
Oh, the second one is the multiple choice true false, which
It's not going to be cut?
there's going to be a sequence of those which are going to be, like I say, you can expect the problems that I cut to maybe be absorbed into multiple choice format or true false format. Okay? Now, so now I'm at question number 8 is cut.
Why don't you talk about it just a little bit?
You want to talk about number 8, the silver bromide?
Well, just a little bit, because I think you're going
We'll talk about it a little bit then. Okay.
Just what you might
Just a little bit.
We'll go back to that one.
Yeah, go back.
It's going to be in a multiple choice format. Let's do it real quick. Okay. Let's go over. I can even use this board, so we don't have to remove the camera.
Oh, yeah.
Ideally, probably it'd be better if we got a blackboard and used chalk for contrast. And I hear Glenn Beck's going to be not needing his soon, so maybe I can get them over here.
donations are good.
Yeah, maybe he's interested in donating. So, calculate the molar solubility.
That was actually on YouTube from last recitation.
That is? That is on YouTube, so you guys could just check that there.
Over the concepts.
I'll just go over the concepts. I'll go over just the concepts. I'm not going to do the whole problem. Okay. And
Concepts you're testing us on.
and what was the molarity? Doesn't matter. And 1.0 ammonia. And I gave you that KSP for silver, or PKSP for silver bromide is equal to 12.30, and PKF for the silver diamine is equal to what? Minus 7.26. Okay, so let's just look at that, and what does that obviously tell me? Well, KSP is going to be equal to what? 10 to the minus 12.3, and KF is going to be equal to 10 to the plus 7.26. Okay, now the first thing you would do in solving the problem is I would have to write these are going to be what kind of equilibrium? Coupled. And how do you couple to equilibrium? Well, how do you couple them?
The products of one is the reactants of another.
Yeah, when the products of one equilibrium is a reactants and another one, they are thermodynamically coupled. Okay? And so the first process is silver bromide. solid dissociating into silver ions plus bromide ions. And the second process is silver ions so formed can then combine with 2 ammonia molecules in solution to give me the complex, the diamine complex of silver. And now I know that K1, let me write this out, K1 is equal to, as we've already said, 10 to the minus 12.30, and K2 is equal to 10 to the plus 7.26. I could even ask you what delta G was for a general ballpark question. Given pK, you can tell me that.
Maybe we should just leave all these questions back in there. Properly studied.
Okay, well, okay.
What do you think?
Well, here we go. So now I'm going to have to add these two together. And what happens when I add them? We've already done this. This is an intermediate. And so I end up with 3 being silver bromide, the overall reaction.
Now, why are we doing this? That should be on it.
What? Okay, now we've already, like I said, we already reviewed all the details on the actual reaction. But what am I going to know? Since I'm adding these two equilibria together, K3 is going to be equal to what? K1 times K2. When I add the reactions, I multiply the mass action expressions, or the mass action constants. What other questions could I ask? Well, obviously, well, I don't know how I would ask this in a question, but I'm gonna, when I hit the ice here, I'm gonna start out with whatever the molarity was here. It's gonna change by how much? Minus 2x because of the stoichiometric coefficient. And then when I get to the mass action expression, it's gonna be 1 minus 2x squared, again, because of the stoichiometric coefficient.
How'd you put that in a true and false?
That's a hard one.
Would it be like anything on the last test we've had, like 1, 2, or 3?
It would be something about the stoichiometric coefficients, or the exponents in the mass action expressions.
As far as preparation goes, it'd be easier if it was like a question from a previous
It's
test.
going to be a general equilibrium. This is
Okay.
more of a test of your equilibrium knowledge, and your knowledge of manipulating those. Basically, we're going to hit the ice with this, and we're going to get a great simplification that comes out of it because it turns out to be a perfect square, but that's all just sort of mathematical hoorah. Okay? I'm not interested in bogging us down with that, particularly because it takes so much time. So I'm going to absorb this into a qualitative question.
Okay.
Yes?
Can you add this problem as an extra credit for anyone who wants it?
Yes.
Well, I'm...
You have the conceptual, but then add it as an extra credit if anyone wants to go through the process of it.
I think that would be a great idea.
Yeah, I think that's an excellent idea.
Okay, so now that it's been cut, now you're lobbying to get it back.
Only for extra credit.
You gotta love everybody here. I'm eating this up with, I got a sweet tooth for this. Okay. So I'm getting a universal consensus
If it's extra credit.
that I put it on as an addendum as extra credit.
60 points.
All of the questions that we have 50 points.
Yes! 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 That'd be great!
You guys are driving me to drink. Okay.
Hey, we're asking. We want to show you our great skills.
I will.
Bring it on.
I will do that.
All the ones you're going to cut.
Okay, wait.
More points.
Okay. I will.
So you guys are still going?
Oh yeah. We're just now discussing one of the problems that was cut, which I've said I'm going to absorb in the multiple choice questions, and now I was asked if I would now add it on as an extra credit question. Now that everybody agreed we should cut it, now they're lobbying to put it back on as extra credit. And I'm agreeing to that.
Okay.
That's awesome. High five, Fletcher.
I don't know. I feel cheap myself. I may be cheap, but I'm also easy. Okay. Okay. Now we will include this or a question like this as extra credit.
How many points?
I don't know.
Worth a decent amount.
It'll be okay. It'll be a 20-pointer or something like that.
Worth your time.
Okay. So, as far as the other ones, I'll include several of the ones that were cut.
I'm going at 4:30 to start this.
Nice.
Because I really don't want you guys to bog down. Because one of the problems was we didn't have enough time to do the whole test. But any of you guys who are ambitious, go for it.
Bring it.
I see no reason not to bring it. Okay. I'm all, it's on.
So when is this final anyway?
I'm going to be, it's on Tuesday, officially from 5:15 to 7 or something like that.
You're going to put the rate law one on there as extra credit too?
Yes. All the ones that I've got are going to be included. Okay. Quiet. The test is also going to be available as of Monday at the Learning Center, so you can go. Anybody who wants to take it early can take it. And when you guys are your Monday hours are from 10:30 a.m. till 9 p.m. So I will drop it off Monday morning. Before that, I'll drop off some copies. I will include a periodic table, and so everything is.
Should we give them Tuesday testing hours too? I mean, are you gonna
Yeah,
do that?
it'll be Tuesday, Monday and Tuesday, because and Tuesday's testing hours are 2:30 p.m. till 9 p.m. And so that might accommodate. There was one individual here who has lots of time, but has another test following this one, and so that would take care of. Will that take care of you? Excellent. So.
Are you giving them time after the test too?
Yeah, I'm going to give you the official test for everybody who wants to show up and take it here. Is 5:15 until we leave.
And I think we're doing that all the way through Friday. We're going to be open for testing.
Okay, so we can have extra time. So I mean people after who can't make it the Tuesday.
Right. Actually, well, we're holding testing hours all the way through Friday. For people that can't finish their finals in time.
Okay. Okay. I'm trying to accommodate as much as we can.
It's up to you.
Okay. Okay, quiet on the set. Quiet on the set. Okay.
Be able to pull them when you go home on Tuesday, because you've given us so much free time of your.
Okay, well, I will let me say this much. Because it's going to be available over there, and I'm not going to be able to go over to the testing center after I'm done here. So at very least, I'll let it go through a Wednesday.
Okay.
So anybody who doesn't make it, because I'm going to come back and pick them up.
Wednesday's good.
And grade those. Because I got to finish the grades or somebody downtown's going to be mad at me for not getting my grades submitted. Okay, so that's the best I can do.
Thank you.
And those of you who come and take it here, I'm not going to have any time constraints. If you want to go, I am going to have to go home that night or my wife's going to give me a hard time. But we'll, within reason.
Do you do the bison that's afterwards?
5:50.